Hello and welcome to this video about why bonds form. In this video we're going to look at the fact that elements combine to form compounds, why atoms form compounds, we'll look at some chemical formulas and what a chemical bond is. When elements combine to form compounds, oftentimes the property of the new compound is nothing like the properties of the individual atoms that make it up. For example, copper and sulfur, as well as oxygen, combine to form this compound, copper sulfate. You can see clearly that this has nothing similar to the properties of oxygen or of sulfur or of copper. Here is another example of elements combining to form something very new. We have potassium right here. It's a shiny, soft, silvery metal, and it reacts violently with water. Iodine, here, it's actually a blue-black solid, and at room temperature it turns into this purple gas. Would you have guessed that they combine to make this white crystalline potassium iodide salt? So, we know that a chemical compound is oftentimes nothing like its individual components, but we do need to be able to write down what the individual components are. And we can do that in what we call a chemical formula. Let's look at what a chemical formula tells us. You're all familiar with this chemical formula, H2O. You know that H2O is water, and you know that we write H for the hydrogen. Here's the symbol for hydrogen. Here's the symbol for oxygen. And you can see this little 2 is written as a subscript. It means it's written small below. And it indicates how many of the atom right before it there are in every compound or every molecule of water. So here we have 2 hydrogens and only 1 oxygen. We do not write a 1 if there's only 1 of any element. So let's take a look at some of these chemical formulas. The common name sand is actually, the chemical name for sand would be silicon dioxide. And silicon dioxide, there's a typo there, should be written like this. Not with a subscript 3, but with a subscript 2. There is 1 silicon, because there's no number indicating a larger number than 1. And there are 2 oxygen for every one of these compounds. Cane sugar, the chemical name for that would be sucrose. And here is what we have for the chemical formula of sucrose. How many carbons are there? 12. How many hydrogens are there? 22. And what do we have here? 11 oxygens. Similarly, acetic acid, which is the acid in vinegar, the chemical formula looks like this. And for the chemical formula this time, they actually separated some of the oxygens and one of the hydrogens. There are a total of 3 hydrogens. There are a total of 2 carbons and 2 oxygens. And it's written this way because of the actual formation. It makes a little bit more sense, and it's easy for chemists to look at it this way. Laughing gas is actually dinitrogen oxide, and its formula looks like this. There are 2 nitrogens and 1 oxygen. So why do atoms form compounds? Well, to look at that, let's take a look at the periodic table. And a periodic table has been shown right here with the transition metals removed, and we're just looking at groups 1 and 2, and then groups 13 through 18. It's a little bit different numbering system than we use. But what is being shown are the electron dot diagrams for all of these elements. And you can see in this first column, there is 1 valence electron in each of the outer shells of each of these elements. Here we have the alkaline earth elements, and they have 2 valence electrons for each of the elements. Here in this group, you can see there are 3 valence electrons, so forth and so on, until we get to the noble gases. And these noble gases, here helium has 2 electrons in its outer shell because that's all its outer shell can hold because it's the first principal energy level. Neon, argon, krypton, xenon, and radon, you can see they have 8 valence electrons. They have full valence electrons, or full electrons in their shell. They are very, very, very stable. These noble gases are incredibly stable because they have full energy levels. So these full outer energy levels in the noble gases make them very chemically unreactive. They're happy the way they are. They really don't want to have anything else happen with their electrons. As a matter of fact, the first noble gas was not even reacted with another element until 1962. They were not able to figure out how to make them react. On the other hand, we have elements like hydrogen that would love to just have the same full shell as helium. It oftentimes gains an electron or loses an electron, either one, depending on what it's reacting with. The rest of these, lithium, sodium, potassium, rubidium, and cesium, they tend to lose that outer electron so that they can be more similar to one of these noble gases with the numbers of electrons that they have. And similarly, these elements oftentimes lose 2 electrons because they would really like to have the same number of outer shell electrons as these noble gases. It makes them very stable. So as you know, atoms can gain or lose electrons. That's what we were just talking about, these losing electrons. These elements right here, the halogens, fluorine, chlorine, bromine, iodine, and astatine, they almost have a full octet. Look at that. Fluorine just needs 1 more electron, and it could have the same number as neon. So these elements tend to gain 1 electron. These elements will tend to gain 2 electrons. You can see they need 2 to have the same number as one of those noble gases. Atoms can also share electrons to achieve this stability of a full octet. And atoms basically gain, lose, or share electrons in order to gain that stability. That is the reason that atoms form compounds. A chemical bond is formed when atoms gain, lose, or share electrons. And that chemical bond is essentially the force that holds the atoms together in the compound. Some advanced ideas use dot diagrams with 1 carbon atom and 2 oxygen atoms to make an arrangement that gives the carbon and oxygen atom each an octet. Also, you may have noticed that we skip the transition elements when discussing how electrons fill orbitals. Research how they might be filling their orbitals. You might look at the different shape orbitals, such as s, p, d, and f, and what their relative energy levels are. You can also look up what quantum numbers are. Tell me a little bit more about those. Electron configurations, what are those? How are they written? What are some examples of electron configurations for different elements? If you have other ideas, please feel free to share those, and I look forward to seeing you in class.